Okay, the next thing we're going to talk about is the squeeze theorem. So stick with me. There are a lot of techniques in this section. So hang with me. We're doing this, but this is covering it, right? So this 2.3 is a big one because it's covering this information. We've got this. So the next one is called the squeeze theorem. Because you can plug it in immediately, right? If you can algebra something down, you do that. If you can't, then we're going to have what's called the squeeze theorem. So here is the actual theorem. We're going to assume the functions f, g, and h satisfy the fact that f of x is less than or equal to g of x, which is less than or equal to h of x, for all values of x near a, except possibly at a, if, and here's the kicker, the limit as x approaches a of f of x equals the limit as x approaches a of h of x, which is L, then the limit as x approaches a of g of x also equals L. Now, if you need to, pause the video so you can get this written down before I keep going, but I'm just going to keep going with this because these are videos and you have the chance to pause them, all right? So here, look at what happened. F of x is the small one. H of x is the big one. So if I have these broken out where f, g is in the middle, and h is the big one. So f is the small and h is the big. If the bottom and the top are equivalent to the same value, right? They're the same limit. That stands to reason what's in the middle, what is squeezed, I can squeeze these together, and then my middle one is also going to be that same value. Okay? Okay, that's the kicker. That's the deal. That's the whole deal. So with the squeeze theorem, typically, not always, sometimes you do some algebraic stuff in here, but typically you're going to have trig. Typically, you squeeze trig. All right. We're going to do some more in Calc 2 when you get into Calc 2 with the squeeze theorem. So you'll do some more with it there also. But this is just a nice introduction to our squeeze theorem. So here's example 8. For our intents and purposes right now, we're just going to verify, using the squeeze theorem to verify these values. So here is our example 8. Use the squeeze theorem to verify that the limit as x approaches 0 of x squared and the sine of 1 over x equals 0. All right? Pardon me. Here's the kicker to the squeeze theorem. The squeeze theorem is what you have. All right? You're building off of what you already have. So whenever I'm looking at this, I'm going to look at this part of it. What do you know about taking a limit of a sine function? Yeah. I'm up here at a 1 and down here at a -1, right? If I'm taking, and it goes both ways, I mean, this just keeps going, right? If I'm looking at this, I'm going to take my limit. I max at 1, keep going and maxing it 2. If I'm looking at sine, just sine here in general, I'm bouncing back and forth between +1 and -1. So a sine function, as I'm approaching on and on here, a sine function is going to go between positive or -1. And here's the other kicker. This 1 over x, that's just that transformation, right? It's just affecting my period is all that's affecting because it's that inside part. So it's just affecting the period. So I know that my sine of 1 over x is going to go between -1 and 1. All right? Then you build on that. So my goal is to have this whole thing and to get it figured out. So if I multiply x squared here, I'm going to multiply this by x squared, the inside by x squared, and the back by x squared. I'm building that up. So I have a negative x squared is less than or equal to x squared, the sine of 1 over x, which is less than or equal to x squared. And here's the whole concept behind the squeeze theorem. The whole concept is I have something that's difficult to look at and mess with. There is no factoring that, right? There is no rationalizing anything about that, right? So because of that, and I know sine bounces back and forth, I got to be careful with it. Because I know that's happening, then you squeeze this so that you can build it up. Now, the squeeze theorem tells me I'm going to take this lower limit. It's just a polynomial, so you plug it directly in. And I'm going to take this upper limit. And if those two limits are the same, then I know my inside limit also has to be that same thing. All right? So then you write, so this is all you have to have on here. So on your paper, you will have the buildup that you've got right here. You take the limit of the lower, you take the limit of the upper. That's all proof of the squeeze theorem. And then you say, therefore, by the squeeze theorem, the limit as x approaches 0 of x squared, the sine of 1 over x equals 0. When you have a proof, you always want to write your therefore statement, right? That's your, hey, here is my proof of what I just showed. Here's my conclusion statement because I proved it with the work I'm showing. Have you seen this before? If you haven't, we're going to see it a lot. A triangle of dots stands for the word therefore in math. Can't remember if we've talked about that already or not. So therefore, by the squeeze theorem, and anytime you prove a theorem, you have to state that theorem. So by the squeeze theorem, this is my conclusion. All right? And you've done all the work up here to show that. And because of the work you have to show it, you can then write your therefore statement, but you have to state the theorem, in this instance, the squeeze theorem, and your conclusion.